And without further ado, let me introduce Emily Halina. Emily is a PhD student of the University of Alberta researching human-centered artificial intelligence. She's interested in procedural content generation, helping designers make games, and her cat, Ruka. She's published work featuring almost all of these interests in multiple top AI and games venues like IJC AI and AID. Before academia, Emily worked as an indie game developer, and as a result, she is particularly interested in helping indie devs make weird, cool games with her research. I think those are interests that a lot of us here share, Emily.
Fantastic.
Awesome.
Great. Thank you so much for the lovely introduction. Hello, everybody. My name, as Rourke said, is Emily Halina, and I'm here to talk to you today about tree-based reconstructive partitioning, or TRP for short. And this is a really exciting new level generation approach where you can generate new levels from a single example. So a little bit already covered in the intro. My name is Emily. I am a PhD student at the University of Alberta, working with Matthew Gusdile in the Grail Lab. If you see Matthew in the chat, please say hi to him. My main research interest is to help people make games. And the way that I want to help people make games is through procedural content generation. And the way that I want to do that procedural content generation is with machine learning. More on that on the next slide. Now, previously, I was an independent game developer, and this sort of informs my position as a researcher as well. I want people to make cool and weird things with my research, and I want to make my research accessible to people who are making games, especially indie devs. Now, all of us have heard of procedural content generation, seeing as we are at Roguelike Celebration, which is a celebration of a genre which is entrenched in PCG stuff. However, I'm going to talk about a couple of different families of PCG today. The first family of PCG that I want to introduce is constructive PCG. And this is the PCG that we're all very, very familiar with and is featured in a lot of games. Essentially, what this looks like is a human designer is going to make a whole bunch of Lego pieces that a generator, which is also authored by a human designer, is going to stick together in various ways in order to build a level or a creature or an art asset or anything else. Today, we're going to be talking about level generation, since TRP is a level generation approach. Now, we've seen constructive PCG in games like Enter the Gungeon, Hades, Binding of Isaac, Slay the Spire, Boyfriend Dungeon, and I could list on and on and on. I could list 20 or 30 games that use constructive PCG. However, there are a couple of issues with constructive PCG. It's not exactly the best system for everything. While it can be super expressive and it can be super lovely and make really beautiful content, somebody has to go and author all of these different Lego pieces, and that can be really intensive. Furthermore, somebody has to author the generator that sticks them together, and maybe you have to add additional information, such as constraint information on these different pieces. Maybe one room can only go in the corner of a dungeon, or one room has to be accompanied by another room. And this can get really complicated really fast. Wouldn't it be great if instead of authoring these pieces, we'd be able to somehow learn from previous levels that a human has made and use that information in order to make new levels? And this is that high-level idea behind PCG via machine learning. Here by machine learning, what I mean is that we're just going to learn patterns from data in order to learn some sort of function. On screen is Townscaper, which uses WaveFunctionCollapse, which is a PCGML algorithm, in order to generate its townscapes. Another example of a game that uses PCGML is Caves of Cud. So I'm sure that many of you are familiar with. But I want to go into a brief aside here, because many of you might have heard machine learning and said, wait a minute, isn't machine learning bad? Well, today we're talking about small models which just learn patterns from data. They don't require any more power than developing a game normally, and there's full consensual use of data here. Maybe one or two levels that we're taking from a human designer who's given us explicit permission to do so. There's no web scraping going on. There's no evil stuff like that, as you can see by this evil neural network on the side here. So if machine learning isn't evil and it's so good, we can learn things, that sounds pretty good. How come on this slide, I didn't have a lot of examples of games that use PCGML? Or in other words, why is PCG via machine learning, why isn't it more popular? Well, a major problem that we've run into is a lack of data within the domain of games. Most machine learning approaches require a ton of training data in order to work. On the left here, we see a neural network-based approach called an autoencoder. When given only 2 Mario levels, it ends up spitting out content that looks like this, which isn't going to be too helpful for either a designer or a player who wants to play an exciting new level. Now, there are other machine learning approaches that require only a single example, like WaveFunctionCollapse, but these can have pretty major drawbacks. In this example, we see a dungeon-like game where there are keys and doors that you have to reach. So you've got to get the key and then get to the door. Well, there's no door in this image. And also these spiders are kind of off in their own chambers, sectioned off. No matter where we put Link or another protagonist in this space, it doesn't really make any sense to navigate. There's no respect for the global constraint of needing to get to a key and then get to a door. Well, wouldn't it be nice if there was an approach that was able to get around these drawbacks and could work with a single example? Well, luckily for us, we have Tree-based Reconstructive Partitioning, or TRP. I'm going to be calling it TRP for the rest of this presentation because Tree-based Reconstructive Partitioning is a bit of a mouthful. The high-level idea behind this approach is that we're going to use playthrough data of an AI agent that's going to play through a level that's been authored by a human, and we're going to use that data that playthrough generates in order to generate new levels. The results here are that we get better coherency of the output levels without strenuous input from the designers. So we aren't asking the designers to author a whole bunch of constraints or specific examples that require you to know how the algorithm works in order to make the most of. We're just asking them to tweak a couple of parameters, which we'll talk about in a little bit. So that's what today's talk is all about. It's all about tree-based reconstructive partitioning and you. We're going to talk about how the algorithm works. We're going to do some comparisons against other methods. And most importantly, we're going to talk about how you can use TRP in your projects and what the future of the algorithm looks like. So let's go ahead and start by talking about how the algorithm works. But first, we need a little aside. The aside is about the domains that we're talking about today. So the two games that we're going to be showing examples from today are Super Mario Bros. For the NES and GVG AI Zelda, which I know are equally popular games. Both are gargantuan in the gaming world. GVG AI Zelda, for context, obviously is not the most popular game in the world, but is a research testbed game. So it's a game that was invented in order to do research with. And in the game, as I gestured at earlier, you control this player character. You're trying to reach a key and then reach a door. And you have a little attack that you could do to kill this lobster guy or this spider guy. Now, some notes about the domains. The domains need to be navigational, meaning that there's a 2D space that we are walking through. More about 3D towards the end of the presentation. And there has to be a specified goal. So this might look like Mario reaching the flagpole in Super Mario Bros. Or reaching the door with the key in GVG AI Zelda. Now, with that out of the way, let's talk about how TRP works. I'm going to go through each of the steps of how TRP is implemented on a high level, and then we'll go into more detail on later slides. The first step of TRP is we're going to play through a source level. This is a level that's made by a human. And we're going to play through it with an algorithm called Monte Carlo Tree Search. Another brief aside about how Monte Carlo Tree Search works. I'm not going to get into the weeds about how this algorithm works, but the important thing to understand is that it generates a search tree as it plays through the level of a whole bunch of possibilities, so a whole bunch of possible futures that MCTS looks at. And it uses this information to decide what best to do. And we could use this search tree information in order to generate a new level. And that's sort of the high-level idea behind TRP. So once we play through the source level using MCTS, the next step is we're going to do a binary reconstruction of the original source level using the MCTS search tree data. So what this looks like is everywhere where Mario has been is going to be empty, and everywhere where Mario hasn't been is going to be block, in the case of Mario. The next thing that we do is we fill in the details of this binary reconstruction. I'm going to hand wave a little bit here because there's an explanation of how this detail filling in works on a later slide. But essentially, the idea is we're going to copy and paste segments of the original level into the binary reconstruction based on some matching. And the last thing that we do is a probabilistic threat placement. Normally it says enemy on the slide, but it doesn't have to be enemies. It could be anything that threatens to end a playthrough of a game. So in Sokoban, a threat might be having the boxes all in the wrong position. Like one's pushed up against the wall and you can't access it anymore. So with these 4 steps in mind, let's go ahead and look at a visualized example of how TRP can generate a level. So here's our original level. This is the second half of 1-1. I'm showing you the second half instead of the first half, just because it generates a more interesting level. The first thing that we do is we play through that level with MCTS, and we're going to get a cavernous representation of the level. So if I flick back and forth between these two, you can kind of see that it's the path through the level, right? So Mario is jumping over these stairs here, and then over these stairs here, and etc. And you can see that there's even a pitch there. Now, after we've gotten this cavernous representation, we're going to split that into different segments. This is split into different size segments at random. So here they all happen to be column big. They don't have to be a column tall. They could be, there could be a line here, for example, but this is just a simple example. Then we're going to use binary space partitioning in order to fill in the details of the level. So these are segments that were taken from the original level that we're going to copy and paste into the new level using a specific matching algorithm. The last thing we do is a bit of probabilistic enemy placement based on that MCTS data, and also a bit of cleanup. So we're going to place down the flagpole in the right place, make sure that Mario's at the start of the level, etc. Make sure that the level is coherent. So to go through these steps in a bit of additional detail, the first step is that we use MCTS to play through the level. And when we do this, we collect data from the MCTS search tree. The two things that we care about here are what path the player took through the level. This is marked in purple. And where the player died, or wherever the game is no longer completable. So that might mean falling in a pit or running into a Goomba. So we're tracking all this information as MCTS plays through the level. The next step is that we reconstruct the original level using this path information. So where the player has been is going to be empty, and where the player hasn't been is going to be full. It's called a binary representation because there's two options here, either 0 or 1. Now, notably, the designer has to say what empty and full are. So they have to say, all right, this tile of like empty space or no tile at all is empty, and this tile is full. Doing this creates a cavernous outline of the level to come. So it's sketching out a path for the binary space partition to use in filling in the details. Speaking of which, the next step is to fill in the details. We fill in the details of our new level using binary space partitioning. Here is a worked example here. We have the original level right up top here and a work in progress level that is at the bottom. And this is a segment that hasn't been filled in yet. All these other segments have been filled in. We just have this one cavernous section remaining. How it works is we're going to take the size of the section that's remaining after dividing up the level into a bunch of small little boxes, and we're going to do a scan of the original level like this until we find the most appropriate thing to match this with. This is based on edit distance, based on what tiles are considered solid and which ones are considered empty. So here we see that we're matching with this like structure with two pipes. And you can see this sort of structure mirrored in the cavernous representation. So you can imagine that maybe the path that we've taken to get here is Mario has jumped off of a pipe here and then jumped onto a new pipe. And that's sort of the matching that's gone on here via edit distance. Once we have the closest match, or if there's a bunch of different matches, we just pick one at random. We're just going to copy and paste this information onto the new into the new level. The last step, and probably the most unnecessary step of TRP, so you don't necessarily need to do this for it to be TRP, is to populate the level with threats. And the idea behind this is we're going to use the threat information from MCTS in order to populate the level. So since we have all that depth information, we might as well use it for something, right? So how it works is until a threshold is reached, this threshold is set by the designer, we add the most impactful threat. And here what I mean by impact is the amount of deaths that a threat has caused. Deaths, again, in air quotes here. Now, an example of this might be if there's two Goombas in a Mario level, maybe one of them is responsible for 75% of the deaths, and the other one is responsible for 25% of the deaths, total across all the deaths that happened during the simulation. So if this is the case, then we're more likely to place this one that has 75% of the deaths than this one, which is only responsible for 25%. So we'll place this one first. And this sort of comes from the notion from game design of placing the most impactful threats in the level while having as little threats as possible. So those are the 4 steps of TRP, but there are also a couple of parameters that we can change with TRP in order to affect the generated levels. The first of these parameters is how many MCTS playthroughs worth of data that we use. So we don't have to just play through the level once. We could play through the level multiple times using MCTS. Generally, if we have more playthroughs, it's going to lead to a less restricted level. And the easiest way to see this is in the binary representation. With 1 playthrough, it looks like this, and with 5 playthroughs, it looks like this. Notably, MCTS is a stochastic algorithm, meaning that it's random, so it'll do something different every time. So that's why we end up taking different paths over different playthroughs. And this might work well if your game has multiple branching paths or things like that that you want to account for. The next parameter is what the minimum size of the segments that we take from the original level are. So here we see that if we're taking bigger segments, it's going to result in more plagiarism. Now, plagiarism is a bad thing in academia, but it might not be the worst thing when it comes to level design. For example, if we look at this staircase here, most Mario levels end with a giant staircase. And it might be weird if our generated level didn't end with one. So in this case, taking a large amount of structure might be a good thing. However, if we go the opposite side of the coin and we take smaller segments from the original level, this is going to result in more chaos. Now, the image on screen might not be the most useful Mario level you've ever seen, but it's still kind of interesting, and it might be useful for a designer, especially if your game, for example, might have more vertical movement. So here we can see that we've taken sections that are not just a column tall, and we've placed some sort of floating air in the sky here. So kind of interesting output that we can get. As well, the last parameter is what percentage of threats that we place in the original level. This could be none at all, or it could be all of the threats that we encountered at all the points. And this, of course, is a spectrum. So we could do it, 25% of the threats or 85, whatever is suitable. And all these parameters, it's really easy to just guess and check and mess around with TRP because the generation process is instant. It is so fast. So you can generate hundreds and hundreds of levels with different parameters and see which ones are best for you. Now that we've gotten the algorithm working section out of the way, let's talk about some comparisons with other methods. Now, in order to do comparisons with other methods, we're going to have to talk about other methods. And you'll notice that I'm going to kind of blitz through this part. But if you're interested in learning more hearing more about these other methods, or hearing more about some comparisons with them, we have a paper about TRP that I've got a QR code linking to later in the presentation. So let's talk about some other methods. The first one I mentioned in the introduction is WaveFunctionCollapse. Notice that I also have sturgeon mentioned here. WaveFunctionCollapse is a constraint-based solver that takes in an example image and uses it to make bigger examples. So this small plant has become big plant by following the same rules that are present in this image. And this is used in multiple indie games like Bad North here. It uses WaveFunctionCollapse. Notably, in the domain of Mario, we compare against sturgeon, which is a level generation approach out of Professor Seth Cooper from Northeastern's lab. We compare against that for Mario because it generated levels faster, and it ended up having a higher quality product to compare against. But it is also a constraint-based solver. So the important thing here is that it's constraint-based. The next approach is Markov chains. And this is a probabilistic approach. I thought this figure looked kind of scary, so I put chains and flames on the slide to make it a little bit worse. Essentially, how this approach works is we have a filter that we're going to look over the level with. In this case, it's an L-shaped filter. And we're going to see if these three blocks are in these positions, what is the likelihood of a block being in the top right position here, or a coin being in that position, or a Goomba being there. And we add up all those probabilities after sweeping the entire level, and we use that, we sample that probability distribution in order to generate new levels. The next two approaches are neural network approaches. And I want to stress that it's not important to understand how the neural network approaches work here. So the first is an autoencoder. Essentially, how this works is we have an encoder and a decoder that are trained to reconstruct input, and we can feed in either noise or the original level into the decoder, and that will hopefully spit out some new levels. The last approach we're going to talk about in today's presentation is called ToadGAN. I don't have a great image of ToadGAN, so we've got a toad plus a GAN, which is a type of neural network. And again, not important, the specifics about how GANs work, but I'm happy to answer questions about it, obviously, if it comes up during that. So in terms of comparison, let's do a comparison of some generated levels for both Mario and GVGAI Zelda. Now, these levels were chosen randomly from a population of 100 generated levels of all the approaches. So we aren't just cherry picking examples here to say, all right, TRP looks better because we picked the best TRP level and the worst sturgeon level, for example. So up top here, we have the original 1-1 for reference. We've got a TRP level generated level for comparison. And these two are going to stay the same between the next couple slides, and the baseline at the bottom is going to change. So we'll talk about each of the possible issues with the baselines. So the first baseline here is sturgeon. We see that there are these giant gaps in the level, which end up making it unplayable. Sturgeon does have a playability constraint built into it, but we ended up turning that off for our generations because TRP does not have a playability guarantee. So we figured it would be an unfair comparison to compare Sturgeon with the playability constraint on. However, even if we did turn that playability constraint on, we notice that there's a bunch of sort of noisy blocks that are placed all around here. And it looks a little bit un-Mario-like. It's very sort of scattered. And we don't see the same kind of structures in TRP. We see much more definite structures like the staircases or the complete pipes or this like sequence of blocks. The next approach is Markov chains. So we'll see that there's some weird stuff going on here. So there's like a half-formed pipe all over the place. There's this weird stair thing going on. The ground is doing weird things, which we don't really see in Mario. And overall, things are just a bit noisier compared to the TRP level. For the autoencoder, I sort of spoiled this one in the introduction, but what the autoencoder tries to do is it's trying to optimize towards the best possible fitting output. And what it ends up optimizing towards is sky on the top and ground on the bottom for Mario, because that's the most common thing that it's seen. You know, this is the most common like chunk of Mario level is sky on top, ground on bottom. So we essentially see that, but with a little bit of noise. Now, lastly, we have ToadGAN, and we see that ToadGAN does do a bit of a better job than the other approaches, but there still is some weirdness going on here. Like we have this weird half-formed staircase. We've got a pipe in the sky and half a pipe here. And we just aren't seeing those artifacts in the TRP levels. And you'll have to take my word for it or go look on the GitHub or at the paper yourself. But most of the TRP levels don't have weird artifacts like this. So with the binary space partitioning, we're able to take the correct amount of size chunks from the level in order to make sure that things are coherent. So that's really cool. So next, let's look at a trickier domain, which is GVG AI Zelda. So here we have the original level on the left, and we have the TRP level, which looks pretty similar to the original level. It's a little bit different, like this wall has moved and is now sort of the entrance is here, and the enemies are in different places. However, the WaveFunctionCollapse level is kind of incoherent. It's the same one that we saw in the introduction. So there's no door to go along with these keys. No matter where you flood filled from with these keys, there would be no way to reach the goal. And that's because WaveFunctionCollapse has no respect for global constraints. So what that means is since it only cares about local constraints in the example image, it doesn't care that like, oh, there should be a key and a door in this level, for example. Whereas TRP sort of encodes this necessity through its design. Similarly, Markov chains are probabilistic, so they also don't care about global constraints, and they also generated mostly unplayable levels. Lastly, we have the autoencoder. And with the autoencoder, it's very, very similar to the autoencoder example from Super Mario Bros., where we have sort of walls on the sides and empty space in the middle. This is the most common thing that it sees when it's trying to generate a level. So some takeaways from this comparison is that TRP balances playability and allows for differences from the original level, while still allowing for the level to actually be playable. TRP generates levels with more logical consistency, especially when it's required for there to be logical consistency in the level, like with the GVG AI Zelda domain. And if you want to see a more empirical analysis where we compare the playability, amount of plagiarism, self-similarity, analyzing how the generated population is shaping up. Shoutouts to Ollie's talk earlier. Then please do check out the paper. And there'll be a URL for this at the end too, so don't worry about scrambling to scan this. So the last part, and the most important part in my opinion, is how can you use TRP in your projects? And what is the future of the algorithm? Well, in terms of next steps for TRP, more domains is an immediate first option. A great question is, could TRP work for a more abstract navigational game, like Sokoban, where the goal is to push the boxes onto the goals? My answer to this is maybe. MCTS certainly works for Sokoban, but I think that we'd run into issues with the binary space partition in a domain like this, where there has to be some sort of logic, because binary space partition, in the end, only cares about those local sections of level. So it doesn't care about the global solvability constraint. So we might find that levels generated with TRP for a domain like this would not be playable, or worse, they wouldn't be interesting. What about in 3D? Now, there was somebody working on a 3D implementation of TRP. Shoutouts to Adam Riddle. Lots of shoutouts in this presentation. So it definitely is possible that it could work in TRP, or that it could work in 3D rather. There's lots of different algorithms for dividing up 3D space that we could use in place of binary space partition, or we could just tokenize the 3D level into a discrete space and then apply BSP in 3D to that. So it's definitely possible. However, in order to get more domains for TRP, it would be great if we had better ease of use for this algorithm, because then people could actually use it and they could actually implement it themselves. Now, if you're interested, there's a GitHub that has all of my code for the Mario example, as well as the GPG-AI Zelda example. But if you want to implement TRP for your own game, let's take a look at what that development process might look like. So here's how you get TRP working by yourself. It's as simple as 4 steps. The first is to implement MCTS for your game. The second is to implement the TRP generation process. The third is to collect some MCTS data by allowing MCTS to play through an example level. And then you can just generate as many levels as you like. It's really as simple as that, right? Well, unfortunately, because of all these asterisks, I have to say that TRP has a lot of problems making it inaccessible. Implementing MCTS for a new game is very difficult. You have to define a reward function to guide the tree search, so saying which states are good and which ones are bad. And that can take expert knowledge in order to design properly, and a lot of trial and error. We have to create a forward model for your game, or just in simple words, a simulator for your game, because Monte Carlo Tree Search requires looking into the future to see what's going to happen and simulating out possible things. This is possible to make for an arbitrary game, but it can be very difficult if your game is not designed for a simulator. As well, running MCTS can take a considerable amount of time, and optimizing MCTS is quite a challenge. As well, the generation process itself is complicated. It's not a walk in the park to implement binary space partition, even if it is a somewhat simple algorithm when you write it out. And there's designer information that you have to encode into the algorithm. Things like what's an enemy, what the goal state is, etc. So wouldn't it be nice if there was a tool that made TRP more accessible? Well, luckily for us, there's a work in progress tool called the TRP tool for Godot, which is a work in progress title. The TRP tool for Godot is a tool for Godot, no way, that implements MCTS to play any game, given the list of inputs, as well as a reward function. And we're going to provide a reward function so that will hopefully work for most games. It implements the TRP generation process and allows users to generate levels as they develop their games, which is my goal here, if we remember at the start of the presentation. I want to help people make games with procedural content generation. And I want PCG to help people expand new horizons when it comes to game development. Now, this work was done in collaboration with Fayaz. Fayaz is a student working with both me and Matthew on this project, and his help has been invaluable in putting this together. So let's go ahead and showcase what the TRP tool looks like right now. And bear in mind that it is, in fact, a work in progress, and especially the UI is a work in progress. So as an example, we built this little platformer in Godot. You can see the character down here is the Godot logo, and it's going to move and jump through this scene. Now we see that there are pits in the scene, and there are these weird staircase structures. So we'd expect that generated levels using this example should have some pits, should have some stretches of flat ground like this, and should have some weird staircase structures. So if we take a look at the generated levels here with the original level in the top right corner, we'll see that after we hit this Perform TRP button, we see that here's a level. Here's another level. Whoa. I'll just let it play. Here's another level. And all these kind of different levels that we can get using TRP. Now, especially because this example is small, the levels are going to look very similar to one another, but it's still enough for ideation, hopefully, is what we're hoping. And we want to see what cool and weird ways people use this tool. So if you would like to be informed when we are running a human subject study using this tool, please scan this QR code. And I will linger here for a moment to say, please, please, please. It is a really small Google form. It is one question, and the question is optional. Literally just, we will email you when we're running a human subject study. So if you'd like to see where this goes, it'd be super, super helpful to explore the future of this algorithm. So in summary, TRP is a cool approach for generating levels using a single example. it generates more coherent levels without sacrificing playability. And if you're interested in the approach, you can check out our paper where we compare against even more approaches than I talked about in this presentation, along with an empirical analysis, or you can check out the GitHub to dive into the code of how this actually works. Thank you so much. I have been Emily Halina, and I'm happy to take any questions at this time.
Awesome. Thank you so much, Emily. That was fascinating. I loved all the shout outs, especially Seth Cooper. Some of my friends are in Seth's lab, so that was a lovely surprise.
Oh, fantastic.
Yeah. We definitely have questions. I have some questions to start with. Do you have to use MCTS, or can you use a different type of virtual player or even human playthroughs for the play path?
Fantastic question. No, you don't have to use MCTS. You do not need to. You could use human playthroughs. You just have to make sure that you were recording the playthroughs in the same way and you're getting the same amount of data from those playthroughs. It might be a little bit more limiting because MCTS does a whole tree of possibilities, right? So the different paths that we've taken might not be as well expressed. So like if there's a level that has 2 possible paths, maybe those wouldn't be shown as well with just one human playthrough if the human just took one path. But you could definitely use like A-star for this. You could use other tree search algorithms. We just chose to use MCTS because we thought it was a good fit.
Awesome. Thank you. Cool. We have some chat questions from Ghost Pepper T. What sort of hardware does this work on?
What sort of hardware does this work on? It is really light computationally. So the most computationally intensive part here is running MCTS. And that can be about as computationally expensive as you want it to be. But the actual generation process happens in an instant, and you can generate 100 levels in like a second on like an average PC. I had this working on a very old, outdated MacBook that was falling apart, and it never had any issues with running the algorithm.
Awesome.
So most modern systems, I would say. More constrained systems, like the ones that were talked about earlier, might be more of a challenge for this because implementing MCTS in those systems might be a challenge, but I would imagine the generation process shouldn't be that bad.
Gotcha. And going kind of back to the MCTS, does this generalize to using multiple source examples?
Yes, it does, and it's really cool. So
awesome.
You could use multiple source examples for the binary space partition. So we could have a population of levels that we are taking segments from in order to make a new level. Or you could use playthroughs from multiple different levels for the same game. So if you want to blend 1-1 and 1-2, we can see what happens. And when I've tried it, it's been really, really cool.
That sounds really cool. That question was from Ubuntu and from Mark Gritter. How much tuning is needed to get the segment size to a range that gives a good result? Is it like very sensitive to different size ranges?
I would say that it depends on the game domain. So for the GVG AI Zelda domain, a smaller section size worked a lot better. And for Mario, the column length size worked a lot better because then you wouldn't see the weirdness with the like stacked chaotic level where there's almost 2 levels on top of each other. So I would say it is a little bit sensitive, but it is really, really quick to tune. So you can generate a couple of levels in like a second with one section size. And if it doesn't work, you go bigger, and then you can just do like a binary search to like find which one is best.
I love hearing that a technique is quick to tune. And that kind of leads into one of my other personal questions. How did you choose the specific domains to use this on? I know like Mario is a classic example. It was really cool to see more than just Mario.
Absolutely. So we started off with Mario because it's sort of like the classic testbed for game AI research. So that was like sort of a good starting point. And because a lot of the approaches that we were comparing against were implemented in Mario. So it was like, yes, we will do Mario too. However, Mario isn't a perfect domain. Like, so for example, in GVG AI Zelda, one of the reasons we picked it is because it has that weird constraint of like, there's a sub goal of getting to the key and then getting to the door. And that could have been a challenge for MCTS. Turns out it wasn't a challenge at all because you could just implement sub goals for MCTS. But we wanted to see in more of like a puzzling domain like this, where there's multiple goals, and also where you retread your steps. Because if we look at that level again, if we recall it, it kind of looks like the background of the roguelike celebration. thing that we're talking on. But you've got to walk to the key and then walk back over that same space. So we wanted to see if the binary space partition would break in any way if this happened.
Gotcha. Yeah, I know I personally would love to see more generation techniques tested in less linear and blocky things like Sonic. I wonder how the binary space partition would do with more like flowy environments like that.
For sure, yeah. It might need changing, but also there is work. Oh, their name is escaping me right now, but there was work out of aid last year of somebody who had like an arbitrary way to make a discrete representation of a 2D level. So we could just use that and then do BSP on that.
Awesome. That was so cool, Emily. I really appreciate it. Do you want to put that human subject study, what's the word for it? The QR code on the screen one more time?
Absolutely, yeah. I will go ahead and share that really quick so that everyone can use it. I should have lingered there for even longer, but here we go. Bam.
Awesome.
And I'll post this in the obelisk as well. I'll probably post my entire slides.
Well, thank you so much, Emily. That was very, very cool. I appreciate your time. I'll definitely be taking a look at using this. It sounds fun to play with.
Great. Thank you so much. I really appreciate it. And this has been an awesome event.